In this video, I'm going to solve this question. Let's start with the first part. Now the thing is that in this question, they have given you two models and then they are asking you questions related to omitted variable bias. Now as per the current curriculum that you have, we think that the first two parts of this question are out of syllabus. The reason being they are asking you about the concept of omitted variable bias, and in part number B they are also asking you to obtain an estimate, but the understanding that is required to answer these two parts is not covered in the sections of the textbook that you are asked to read. So basically according to your syllabus, for model specification, you have to read section number 7.1 from textbook by Gujarati. Okay. And you have to read section number 6.1 from the textbook by Christopher Dougherty. Now see, this section that you have over here, section number 7.1 from Gujarati, is not at all sufficient to answer this question. And the section that you have over here from this textbook is sufficient to answer the part number C of this question, but even that is not sufficient to answer the part number A and B of that question. In fact, you can write a couple of lines in the part number A, but part number B is something that you won't be able to do after reading these two sections. So what I'm going to do is that I'm going to show you the answer to part number C from this textbook, and I'm also going to give you a quick overview of the concept of omitted variable bias. So let me first give you a quick overview of the concept of omitted variable bias. So let me write a couple of equations to make you understand this concept. Let's say that this is a true model. So let's say in the true model you have yi equal to beta 1 plus beta 2 x2i plus beta 3 x3i plus some error. So let's say this is the true model. This is the model that you should have worked with. So you should have taken two independent variables on the right hand side, x2 and x3. But let's say for some reason you did not work with that model. You actually ended up fitting this model. So beta 1 plus beta 2 x2i plus error. Okay. So let's say this is the model that you should have worked with. So you should have taken x2 and x3, both of them in the model. But instead of working with that model, you ended up working with this model. So the thing is that you have omitted x3. Okay. Now the question that we have to answer is that if you estimate the parameters of this model, that means if you estimate beta 1 and beta 2, let me call the estimators as b1 and b2. So the question that we have to answer is that are b1 and b2 going to be unbiased estimators or not? So are b1 and b2 going to be unbiased estimators or not? Okay, so that's what we have to talk about. Now see, I'm going to write two conditions over here. If those two conditions are satisfied, that means b1 and b2 will not be unbiased. So let me first create some space over here. So what I'm saying is that there are two conditions. The first condition is that the excluded variable, that is x3 in this case, has a direct impact on the dependent variable, which is y in my example. Okay, so if the excluded variable x3 has a direct impact on the dependent variable y, that's your first condition. And the second condition is that the excluded variable, which is x3 in my case, is related with the included variable. So what is the included variable in our case? The included variable is x2. Okay, so I've included x2 over here, but I have not included x3. So x3 in my example is your excluded variable and x2 is your included variable. So the first condition is that the excluded variable should have a direct impact on the dependent variable. And the second condition is that the excluded variable is related with the included variable. If both of these conditions are satisfied, then your estimators b1 and b2 are going to be biased. So it's not necessary that if you omit a variable and estimate this model, then the estimators are always going to be biased. They are going to be biased only if these two conditions are satisfied. You can very well have those type of cases in which you omit a variable and you estimate a particular model, and still there is no biasness in the estimators. So for biasness to happen, both the conditions have to be satisfied. If any one of these conditions is not satisfied, then you will not have biasness. Your estimators will remain unbiased. Now see, I'm not diving deep into this concept. This is just a quick overview of the concept of omitted variable bias. So the concept is that if you omit a variable, then it may happen that the estimators that you find are not unbiased anymore. They might become biased. So it's not a surety that it's going to happen, but it may happen. It's a possibility. Okay. Now I'm saying it once again, I'm not going deep into this concept because even in the sections that they have recommended you in the textbook, this concept is not discussed in a detailed manner in those sections. So even I'm not going to do that, but I just wanted to give you some sort of summary so that you have something to write if something like this comes up in the exam. Okay, so that's what you mean by the concept of omitted variable bias. The part number B is something that you can totally skip. And the answer to part number C is clearly written in section number 6.1 of the textbook by Christopher Dougherty. So in the part number C, they are asking you to compare the consequences of including an irrelevant variable in the model and excluding a relevant variable from the model. So let's take a look at the section number 6.1. So as you can see over here, this is your section number 6.1 model specification from the textbook by Christopher Dougherty. Now see, in this section, there are only 2 or 3 paragraphs. I would suggest you to read these 2 or 3 paragraphs. The summary of these 2 or 3 paragraphs is there in your table number 6.1. But still, don't just read the table, read these 2 points also that are given over here. So over here, they have written that if you leave out a variable that ought to be included. So this is the case of omission of a relevant variable. Then the regression estimates are in general, but not always biased. See, this is the concept that we discussed, that if you omit a relevant variable, it may happen that the estimators that you're going to get will be biased. But that doesn't mean that they will be biased for sure. For biasness to happen, those 2 conditions that I had written should be satisfied. Okay. And in the second point, they are talking about what happens if you end up including an irrelevant variable in the model. So if you include a variable that ought not to be in the equation, that means if you include an irrelevant variable in the equation, then the regression coefficients are in general, but not always, inefficient, but not biased. So let me make you understand what is it that they are trying to say in point number 2. See, if you omit a relevant variable, that is in point number 1, then there is a risk that your estimators might become biased. And that's a bad thing to happen. But if you include an irrelevant variable, by irrelevant variable I mean, take a look at this table. In this table, the true model is this: y equal to beta 1 plus beta 2 x2. But if you end up fitting this model, so if you fit this model in which you have taken x2 and x3, that means you have included an irrelevant variable, because in the true model, there is only one variable on the right hand side, that is x2. So that is the model that you should have worked with. But if you end up working with the model which has x2 and x3 on the right hand side, that means x3 is an irrelevant variable. So if you work with this kind of model, then these estimators that you're going to find, B1, B2 and B3, these are still going to be unbiased. So if you include an irrelevant variable, then the estimators do not become biased, they still remain unbiased. But that doesn't mean that there is no cost of including an irrelevant variable. There is a cost, and the cost is in the terms of inefficiency. If you include an irrelevant variable, then you are introducing inefficiency in your model. So your estimators still remain unbiased, but they become inefficient. Inefficient in most of the cases, not in all the cases. There is a case in which even if you include an irrelevant variable, the estimators are still going to be unbiased and efficient. But that's only one case. Okay. Generally speaking, if you include an irrelevant variable, your estimators will be unbiased. There is no doubt about that, but they are going to be inefficient. I'm not sure how much of this is making sense to you, because these are important topics: omission of a relevant variable and inclusion of an irrelevant variable. And I just cannot explain you these topics in like 5 minutes. But I hope you have at least got some idea from this video that what do we mean by omitting a relevant variable and what do we mean by including an irrelevant variable and what could be the consequences. Okay. So that was the part C that we just discussed, that compare the consequences of including an irrelevant variable in the model and excluding a relevant variable from the model. Okay, so you can read it again from section number 6.1 of that textbook. So now let's move to the next part of this question. Using the time series data for 1979 to 2009 for a certain economy, the following model of demand for money was estimated. So in this model, MD is your quantity of money demanded, measured in billions of rupees. Y is national income, measured in billions of rupees. INT rate is interest rate in percent on 3-month treasury bills. And this table that we have over here has the estimates of the coefficients and their standard errors. So this is the value of B1. This is the value of B2. This is the value of B3, where B1 is the estimator of beta 1. B2 is the estimator of beta 2, and B3 is the estimator of beta 3. Okay, so these are the values, and over here this is your standard error of B1, this is your standard error of B2, and this is your standard error of B3. Okay, in the part number A, they are asking us to interpret the slope coefficients. Now notice that they are asking us to interpret the slope coefficients, so I'm not going to interpret beta 1, I'm only going to interpret beta 2 and beta 3, and we are also given the values over here. It's 0.530 and minus 0.0261. So I'm only going to interpret these two and not this. So let's take a look at the interpretation now. First, let's interpret 0.530. So in this case, 0.530 means that if we increase the national income, so if we increase the national income, that is denoted by Y, by 1 unit, then on an average, the quantity of money demanded, which is denoted by MD, will increase by 0.530 units. Now see, this is a basic interpretation, but there are three things that I need to change in this interpretation now. The first thing is the units. So I have written that if we increase the national income by 1 unit, you just cannot write 1 unit over here because it's mentioned that the national income is measured in billions of rupees. So the 1 unit is going to be 1 billion rupees. Okay, so instead of writing 1 unit, you have to write 1 billion rupees over here. Similarly, in this case, you cannot write 0.530 units over here. The unit of quantity of money demanded is also billions of rupees. So you have to write 0.530 billion rupees. Okay. And the third thing is that this is a multiple linear regression model. So whenever you do the interpretation, you have to hold the other variables constant. In this case, the only other variable that we have is interest rate. So I can write over here, holding interest rate constant. Okay, don't forget to hold the other variables constant, otherwise you will end up losing some marks for that. So that's the interpretation of 0.530. Now let's interpret minus 0.0261. Actually, let's do one exercise over here. Before I interpret this for you, I want you to pause this video for half a minute and try this interpretation on your own. I'm saying this because I've seen many students making a mistake in this kind of interpretation. Let's see if you make the same mistake or not. So pause the video for half a minute, write the interpretation, and then come back to see if you got it right. So let me interpret it now. So in this case, minus 0.0261 means that if we increase the interest rate on 3-month treasury bills by 1 unit, then on an average, the interpretations are always on an average basis, the quantity of money demanded will decrease by 0.0261, holding other variables constant, in this case holding national income constant, okay, because that's the only other variable that we have. So holding national income constant. Now there are two changes that I need to make over here. I need to change these units. I should have written 0.0261 units, okay, but the unit of quantity of money demanded is billions of rupees, so I should write will decrease by 0.0261 billion rupees. Okay, so I should write that over here. And note that I've written decrease because there is a negative sign over here. Now the last thing that we have to discuss in this interpretation is that what is this unit? So I'm saying if we increase the interest rate by 1 unit, what is this unit? Let's see. It's written over here that we are measuring the interest rate in percent. So what do you think we should write over here? Do you think that we should write 1% over here? Or do you think that we should write 1 percentage point over here? Well, the right answer is 1 percentage point. You should not write 1% over here. You have to write 1 percentage point over here. And these two things are not one and the same thing. Let me explain you what's the difference between 1% and 1 percentage point. And let me create some space over here for that. See, think of it in this manner that over here I write 1 percentage point increase. And over here I write 1% increase. And let's say to start with, the interest rate that we have is 5%. Okay, so this is the interest rate that we have to start with. Now, if I increase the interest rate by 1 percentage point, this means that the new interest rate is 5% plus 1%. This is equal to 6%. So in this case, I'm increasing the interest rate by 1 percentage point. So I'm just adding 1%. But if I increase the interest rate by 1%, that means I will do 5% plus 1% of 5%. In this case, I'm not going to add 1% as a point. In this case, it is a 1% increase. That means it's going to be 5% plus 1% of 5%. That means it is going to be 5% plus 1 over 100 multiplied with 5%. That means it's going to be 5% plus 0.05%. And this is equal to 5.05%. So if you are starting with 5% and you increase your interest rate by 1%, that means you will end up with 5.05%. But if you increase your interest rate by 1 percentage point, that means you will end up with 6%. Okay. So in the interpretation that you have to increase the interest rate by 1 unit. That means you have to take it from 5 to 6. Okay. So this is the reason in the interpretation, you're not going to write 1%. You're going to write 1 percentage point. Okay, that's the solution to part A. Let's move to part number B now. In part number B, we have to test the overall significance of the model at 5% level of significance if coefficient of determination reported for the model is 0.519. First of all, what do we mean by coefficient of determination? Well, this is R square. So you are given that R square of this model is 0.519 and you have to test for the overall significance of the model. That means your null hypothesis is going to be that your entire model is useless. Well, that means I can write that your null hypothesis is beta 2 equal to beta 3 equal to 0. Now again, note one thing over here, that in the null hypothesis, I'm not writing beta 1. Because the significance of the model actually depends on the independent variables that you have in the model. Because only the independent variables have the power to explain your dependent variable. So that means whenever we say that we want to test for the overall significance of the model, that means we want to test whether the coefficients of all the independent variables are 0 or not. If the coefficients of all the independent variables are 0, that means your model is completely useless. Your independent variables have no power to explain the dependent variable. So don't do this mistake of writing beta 1 over here. Beta 1 is the intercept. While testing the overall significance, you just write the coefficients of your independent variables over here. And now there can be multiple cases in your alternative hypothesis. Your null hypothesis is saying that beta 2 and beta 3, both of them are 0. So your alternative could be that beta 2 is equal to 0 and beta 3 is not equal to 0. Or beta 2 is not equal to 0 but beta 3 is equal to 0. Or both of them are not equal to 0. Okay, but see, in the exam, you don't have to write all of these. You can just write at least one of them is not equal to 0. So if you write at least one of them is not equal to 0, then all these 3 cases will be covered. Okay, now because this is a case of multiple restriction, we have 2 restrictions in this case. And how do we know that we have 2 restrictions in this case? Once again, let me remind you that to find the number of restrictions, you have to calculate the number of equal to signs that are there in the null hypothesis. So in this case, how many equal to signs do we have in the null hypothesis? 1, 2. That means there are 2 restrictions. Okay. So because we have multiple restrictions, we are going to work with F-test, and we have a direct formula that we can use to test for the overall significance of the model. That formula is R squared divided by K minus 1. And this whole thing is divided by 1 minus R square divided by N minus K. Note that this is K and this is R. Okay, so 1 minus R square and this is N minus K, where K is your total number of parameters that you have in the model. And when I say total number of parameters, I mean you have to include the intercept term as well. So including the intercept term. Okay, so k is not your total number of independent variable, it is your total number of parameters. So how many parameters do we have in this case? We have 3 parameters, beta 1, beta 2, beta 3. That means k is equal to 3. So let's put values into this formula. The r square that we are given is 0.519. So 0.519 divided by 3 minus 1 divided by 1 minus 0.519 divided by n minus k. Now the next question is, what is n? We are given over here that we have time series data for 1979 to 2009. So 1979 to 2009. And as nothing is mentioned, we can just assume that the data that we have is annual data. That means we have one observation for 1979, we have one observation for 1980, we have one observation for 1981, and so on. If we imagine the data in this manner, then what do you think our n should be? Is it going to be equal to 30? Well, no. And that's also one of the classic mistakes that many students do. You have data from 1979 to 2009. That means you're going to include 1979 as well and 2009 as well. In this case, your n is going to be 31 because both of the years are going to be included. So 31 minus k, which is 3. And if you solve this, you will get that this is equal to approximately 15.17. So your f calculated is equal to 15.17, and now we can take a look at f table to find the critical value of f. We are given that we have to work with 5% level of significance. We are also given the numerator degrees of freedom. This is your numerator degrees of freedom because the numerator is divided by this. So your numerator degrees of freedom are 2, and because your denominator is divided by 28, so your denominator degrees of freedom are 28. So you have to take a look at the f table with 2 degrees of freedom in the numerator and 28 degrees of freedom in the denominator. So this is the f table that we have. If you see, 2 degrees of freedom for numerator is over here and 28 degrees of freedom for denominator is over here. So there are 4 values that are written over here, but it was mentioned in the question that we have to work with 5% level of significance. That means the value that we are going to work with is 3.34 because this is the value corresponding to 0.05. Okay, so the f critical in this case is 3.34. So f 2, 28, 0.05 is equal to 3.34. This is the way you write critical value. 2 is your numerator degrees of freedom, 28 is your denominator degrees of freedom, and this 0.05 is the level of significance. So this value is equal to 3.34. The calculated value is greater than the critical value. That means we reject the null hypothesis. Okay, that means we reject this. This implies that our model is not completely useless. It has some significance. Okay, and that's it for this question.